Hi there, students. This is Mrs. Brunk again, and we've made it to the end of Module 3. We've been studying all about transformations in the coordinate plane and looking at the rules for reflecting, rotating, translating, and even dilating, or even maybe just doing vertical or horizontal stretching. And we are kind of looking at the different transformations that produce what are called congruent figures. And we said it was any combination of rigid motion. So any reflection, rotation, translation, or any combination of those three would produce figures that are congruent. But what does congruent mean? So congruent means that essentially that the figures look exactly the same. They're just in a different spot. But what it really means is that the corresponding sides and the corresponding angles are the same measure. And so in this lesson, we are going to look at what's called the corresponding parts of congruent figures theorem, and we're going to be applying that. And hopefully by the end, we'll be able to identify congruent parts of figures, knowing that the figures are congruent, and B, we will be able to find the measure of a side length or an angle measure using the CPCFC. Sometimes you'll hear it say, and I might say it, CPCTC, which is corresponding parts of congruent. Triangles are congruent, but since they may not be triangles, the F stands for figures. So you can really use it for any kind of figures that are congruent. So this is a really important theorem, and it's a theorem that will have lots of uses as we continue studying about different geometric figures, and it is used to help us extend a lot of learning about geometric figures to learn new things about them. So the corresponding parts of congruent figures are congruent theorem says if two figures are congruent, so then remember that's called the hypothesis. So if two figures are congruent, then what must be true is that the corresponding sides are congruent and the corresponding angles are congruent. So the matching sides would have to be the same length and the matching angles have to be the same angle measure. So first we're going to take a look at an example of how we might apply that to find some missing parts in some, in this case, triangles that we are told are congruent. So in example 1, we're told that these two triangles ABC and DEF are congruent. It says find the given side length or angle measure. Well, in the last lesson, we talked about these corresponding vertices statements that we make about figures being congruent, and we say that the order that they're listed in is how the points match up under whatever transformation it is. And so, for instance, A would have to go with D, B would have to go with E, C would have to go with F, and so on. And so if, let's say, I was asked to find DE, it would actually be corresponding, so CDE is right here, right? It would be corresponding to AB. So that's the first thing they ask us to do, is they want us to find DE. And what I know for sure is that it has to be the same as AB according to this CPCFC theorem, because those are the corresponding or matching sides. So over in our figures, DE is what I'm trying to find, but AB is the same exact length. And look, oh, we already know what AB is. And that means that DE must be the same as AB, which is 2.6 centimeters. So that's pretty easy, right? Next, they want us to find angle B. Well, angle B would have to match up with the measure of angle E. So if we look at these in the drawing over here, angle E is right here, and angle B is over here. They want us to find angle B, and we know what angle E is, so they have to be the same. So angle B would have to be 65 degrees, because it's the same as angle E. So let's say they had also asked me to maybe, I don't know, find AC. Well, all I'd have to do is look over in the other figure, and I can see that AC, according to the congruent statement, would have to go with DF, and look, DF is listed right here as 3.5 centimeters. And we'd also be able to find the angle that goes with angle F, because it's corresponding to C, that would be 42 degrees. And the one that corresponds to angle D, which is A, that would be 73 degrees. And so just knowing that these are congruent, we can take and apply any of the measures, angles or sides, to the other triangle as well. So now that we know how to read a congruent statement, and we know that these two triangles are congruent, let's make question B be a your turn, or you try question. And this is one where you can test your understanding. So pause the video now, and then tune back in once you give these two questions a try. Well, they want you to find two different parts a try. So this is a chance to test your knowledge and see if we're to that point where we've mastered this essential question. Okay, let's see how you did. SU is the same as VX, which was labeled on the other triangle as being 43 feet, and angle S would have to have the same measure as angle V, which was labeled as 38 degrees. So the measure of angle S must equal 38 degrees. So as we've been saying, rigid motions preserve length and angle measure. So rigid motions preserve length and angle measure. This means that congruent segments have the same length. So UV is congruent to XY implies that UV is equal to XY. In other words, segment UV being congruent to segment XY implies that the distance between U and V is the same as the distance between X and Y. Those really mean the same thing, they're just read differently. One is talking about the physical segment themselves being congruent, and the other is saying their lengths are the same. In the same way, congruent angles have the same measure. So the measure of angle J would be congruent to the measure of angle K, implies that, angle J being congruent to angle K would imply that the measure of angle J would equal the measure of angle K. And again, and vice versa. So if the angles themselves are the same size and shape or congruent, in other words, they'd have the same measure. This is a point where we're going to pick up on some properties that we learned in the first module. We're going to kind of extend them out to congruence. We learned that they were properties of equality. They were the reflexive, the symmetric, and the transitive property. And we said they were of congruence. But notice these say they said of equality, and we're saying these are congruence. So the reflexive property of congruence says that a segment is congruent to itself, just like the reflexive property of equality said something is equal to itself. And so again, that just really means something is congruent to itself, which is sort of obvious. And most of these properties are not really difficult to believe that they're true. They're pretty obvious things. The symmetric property of congruence, basically, just like it was with equality, says you can take a congruent statement and reverse it, and it's still true. So if we say that segment AB is congruent to segment CD, then we can also say that segment CD is congruent to segment AB. So it's just an equality statement and a congruent statement. Both can be just turned around, and they still mean the same thing. And then the transitive property. Now, the transitive property says if two things are both congruent to the same thing, they must be congruent to each other. As in this particular statement, if AB is congruent to CD and CD is congruent to EF, then AB must be congruent to EF. So in other words, I like to call this kind of like the linking property, because see how they both have CD in common? And it's a way of saying if they're both congruent to CD, then they must be, logic would tell us they must be congruent to each other. And so I kind of think about that as like a chain link or a linking property. And again, transitive property just says two things equal to the same thing or congruent to the same thing must be congruent to each other. And we're going to utilize some of these properties as we begin to get a little more into proofwriting. In this next example, we're going to apply this idea of congruent parts being corresponding parts in congruent figures being congruent. And we're going to involve a little bit of algebra along the way. So it says that triangle ABC is congruent to triangle DEF. So we've got these two triangles. We know how their vertices line up. And they want us to find segment AB, which is right here. And they also want us to find the measure of angle D, which is right here. So, first of all, to find the measure of segment AB. Well, I know that AB, and actually I'm going to erase this right here, yep. And I'm going to look for AB first. So I know that AB would have to go with DE. So I know these two are congruent segments because of the statement. And so I know they must be equal in measure. And so what I could say is that segment AB, which is 3x plus 8, must equal the other segment, DE, which is 5x. And that gives us a pretty simple equation to solve. So once we employ our algebra skills to subtract 3x, that gives us 2x is equal to 8, or 8 equals 2x. Again, it doesn't matter which way we write that. We can flip it around if we want because of the symmetric property. And when I divide by 2, I get x equals 4. So now they wanted me to find the length of AB, so all I have to do is take and plug 4 in for x in that expression, and it'll be 3 times 4 plus 8, which would be 20 inches. Okay, so segment AB is 20 inches. And then next, they wanted me to find the measure of angle D. So angle D is right here. It's labeled as 6y plus 2. And D corresponds with angle A, which is labeled as 5y plus 11. So I could say that those two expressions, 6y plus 2 and 5y plus 11, must be equivalent because they're congruent triangles. And so they're congruent angles, and therefore their measures are the same. And so when I go to solve this, I would subtract 5y from both sides, which would leave me with 1y plus 2 is equal to 11. Subtract 2 from both sides, and that leaves me with y equals 9. And now to find the measure of angle D, all I have to do is take that 9, plug it into that expression, 6 times 9 plus 2, so that's 54 plus 2, that's 56 degrees. Sorry about my dog snoring again. You just have to bear with me. She is a sleeper and a snorer, big time. So this gives us one for you to try, where we have two quadrilaterals, G, H, J, K, and L, M, N, P, that are said to be congruent, and they want you to find the length of LM, so just help you to kind of identify what we're looking for, LM, and we're also looking for angle H. So I'm looking for this angle right here. Okay, so pause the video now. Do your best to work through and find these two measurements, and then tune back in to see how you did. So maybe when you told someone that you're taking geometry who's already had geometry, they mentioned writing proofs. Well, this is the point where we're going to start really looking at writing some proofs. And we're going to write some proofs that involve using corresponding parts of congruent figures, which was, again, the focus of this lesson. So this is actually a proof that's already been written for you, but it's just to kind of model what a two-column proof might look like. And just the simple steps that you go through to prove something. So we're given this drawing, and we're told that triangle ABD, so we've got this triangle ABD, this one right here, and we're told it's congruent to this triangle over here, which is ACD, this one right here. And we're told they're congruent. And we're asked to prove that D is the midpoint. They want us to prove that that point right there is the midpoint of the segment. So remember back when we studied midpoints in the first module, we said that it was the point that divided the segment into two equal parts. Well, if you kind of just think and reason through, which is really what a proof is, you know that D has to be the midpoint because these segments on either side have to be the same length because they're the corresponding parts of those two triangles, which we're told are congruent. So that's sort of how you write a proof, is you kind of think about where you want to be when you're done and sort of reason backwards, like, in order for me to prove this, what would I have to show? And you kind of just work your way backwards. So taking a look at this, the steps they used, the first step was to state the given information. So so there's two columns. One has the statements in them, and the other column has the reasons, like maybe the property that supports it. And remember, we did these in Module 1 with some algebraic proofs, just like solving some equations, and then we would give reasons like addition, property of equality, and stuff like that. So since we know that what we're trying to do is prove that D is the midpoint, and we know that the segments on either side are congruent, which remember we can show by putting little matching tick marks, that would be my next step. My next step in the proof would be to say that those segments are congruent. And how I know that is that corresponding parts of congruent figures are congruent, or the CPCFC. That's the abbreviation for that. You could also use that to write your proof. And so since we know those are equal, then now it's the logical next step is to say, well, then D has to be the midpoint, and that's because now it meets the definition of a midpoint. So this is a really simple 3-step proof to show that in this drawing D is the midpoint. So this next one we'll actually see if we can come up with the reasons. Okay, the statements have been made of what the things we're trying to say in the proof, and then we just have to give the reasons. So we've got these two quadrilaterals, and we're told they're congruent. Now additionally, and sometimes they'll give you more than just one thing, they told us that angle J is congruent to angle K. So these are in the same figure. So in the same figure, they're saying these little angles in here are the same measure in this one quadrilateral. But then we're told that the two quadrilaterals themselves, the two separate ones, are in fact congruent to each other. And the question that they ask is, can you prove that J, angle J, this one right here, is congruent to angle P? Well, first of all, if I look at the congruent statement, I can tell that J has to be congruent to N. And that's because, look, they're in the same order in the congruent statement. So J is the first letter, and N is the first letter in its name, in the other quadrilateral's name. And so we know J and N are congruent, so we can say that. We also know for a fact that K and L, or not K and L, excuse me, K and, let's get a different color, K and P are congruent. And so that next statement that they made was that. They said that K and P are congruent to each other. So, well, first of all, we didn't give our reasons. Well, the first two reasons were given. So these were given to us. See, they were, J is congruent to K is right there, and then the quadrilaterals are congruent. So these are both given. So if there's a lot of information given, sometimes you might have more than one line in your proof. Now, the next thing they went on to say was that K and P, and by the way, you notice I also marked the given information on the drawing. So when they told me that those two angles were congruent, J and K, I marked them. And now I'm also going to mark that K and P are congruent because those are, sorry. So these were marked congruent. And now I want to mark that K and P are congruent. Well, K is already marked like this, so I'm going to mark it again like that. And P are congruent. And the reason why is those are the matching parts of the two congruent figures. So that's the CPCFC property. Corresponding parts of congruent figures are congruent. And so now, because we know that what we're trying to prove, remember, was this one right here and this one right here are congruent. Well, I know that J and K are congruent. I know K and P are congruent. So if you look back, you see how they have something in common here? They both, J and P, are congruent to K. And so we can link those two statements together to say J is congruent to P using the transitive property. So remember, if we look back at our notes, we just looked at that, and we saw that the property that links right here, see that one? That links two congruent statements together by having a common piece or a common, in this case, segment, then we can prove that in fact the other two things are congruent as well. So that's the transitive property. Okay, let's look at another one. Now this time we're not given any statements at all and only given one reason, and that was the given. Of course, that's the easy one. So now we're going to see if we can author our own. So first of all, the given. So they said that triangle SVT is congruent to triangle SWT. And so we know that because these two triangles, we had the one on top, this one right here, and we have the one on the bottom down here. These are said to be congruent. So we know that there's all these matching parts that have to be congruent in them, right? So it just depends on which ones I want to say in my proof. Well, eventually what they want us to prove is that this line right here is the bisector of angle VSW. So VSW, they want us to prove that that line right there, that segment ST, is the bisector of it. Well, if I could prove that these little angles on either side were congruent, then I would know that has to be the bisector. Well, I can say those angles are congruent. I could say angle VST is congruent to angle WST, and that's because they are corresponding parts of congruent figures, and that means they have to be congruent. So I use the CPCFC property to show that those two angles are congruent. Now I can prove what I was trying to prove, which is always your last step in your proof, that ST bisects angle VSW. And that's because it meets the definition of angle bisector. So essentially what you're doing is you're just trying to find a way to explain what you're trying to prove is true to some other person reading your proof. And you're just giving like a set of logical steps and sometimes there's really like just one way to do it. Like in this case, we had to prove those two little angles were congruent so that we could show that was the angle bisector. But sometimes the body of the proof, there's different things you could have put in there that, you could use as supporting evidence as well. But, it's the shorter the better. I mean, if we can get to it as quickly as possible, just a real direct route, like in this case, just, hey, we could have shown other angles were congruent. I could have shown that these little angles down here were congruent. I could show that these sides were congruent. None of those mattered, though, to this proof. They were not essential, so I didn't bother putting them in there. It's just extra stuff that I didn't really need to write. So I just try to get to the point as quick as possible, and that's considered to be an elegant proof. And one final proof, just for good measure. And just the more that you see of these done, the easier things will get. You'll just understand the process better. So one more for the road. So again, we have two quadrilaterals that we're told are congruent. These appear to be squares, but we don't know for sure. ABCD is congruent to EFGH. So again, you have these matching order of vertices. A goes with E, B goes with F, C goes with G, and so on. And so that would be one of the things, and maybe rather than rewriting, I'm just going to bring this down here and put that right on that spot. And so we know that what is given, and it looks like maybe I need I think I need one more line here to make quite enough spaces. So I think I'm going to draw one more box here. See if we can get one more line. We need at least one more line. Because we have two pieces of given information we're going to write. So we can write the two quadrilaterals are congruent. We also know that AD is congruent to CD, excuse me. So I'm going to mark these congruent on the figure, and that's within the same figure, AD and CD are congruent. So not only are the two separate figures congruent to each other, but within this one quadrilateral, these two sides that are next to each other are congruent. So that was just given information. But what we're actually trying to prove is that the sides, I'm going to highlight them in yellow here, that sides AD and GH are congruent. Well, I actually know for sure, because based on how the vertices match up, that AD and EH, so again, AD would be like the first and last of the name, and then EH would be the first and the last, so those would go together. So I actually know that those are congruent. So I'm going to go ahead and say that. I'm going to say that AD is congruent to EH. I know that, but I also know that DC is congruent to HG. Oops. So see, I know that AD and CD are congruent. That was given. I know that these two pairs of sides are congruent, amongst other things. I mean, there's lots of other things in these figures that I know are congruent because of the corresponding parts of congruent figures are congruent theorem. So I know that these AD is congruent to EH. I know DC is congruent to GH. And what I'm actually trying to prove is that AD is congruent to GH. And now I can say that I can make this connection by showing that, here we have the link between these two, right? And then I also have the link between the DC and right here, GH. So then I could be able to put these two together, the AD and HG or GH. I guess I wrote them in the wrong order. But then I could show that these two link together. Again, that's the transitive property. So anytime that it seems like we're kind of going at it indirectly by showing that two things are both equal to the same thing or to equal things, then we can show they're equal to each other. That's when you know you're using the transitive property. So that does it for today's lesson. Thanks for coming to class.